Hi everyone, this is the demonstration of DisLLM, distributed LLM for privacy assurance in resource-constrained environments. Nowadays, large language models are widely used in many AI applications, but their limitations are not yet addressed completely. As key limitations, deploying LLMs on resource-constrained devices is challenging due to their size and high computational needs, and sending client data to remote servers for fine-tuning purposes also raise privacy concern. This creates a need for a novel framework. DisLLM, our novel framework, addresses LLM fine-tuning in resource-constrained environments while ensuring the data privacy. It integrates federated learning and split learning together and keeps client data only on client devices to assure the privacy. It also uses LoRA to increase computational efficiency and included local differential privacy with control noise to enhance the privacy. Let's understand how the model splitting would take place. Initially, we will have the full model from which we will select a particular cut layer. From that cut layer, the model will be split into two parts. One with lesser weight model will be assigned to client devices and the other will be assigned to server side. Let's move into the DisLLM architectural process. The DisLLM process starts by assigning pre-trained weights to a large language model, which gives the model the basic language understanding capability. Next, we apply LoRA to our model. This is a parameter-efficient fine-tuning technique which reduces number of trainable parameters in the model. And then LLM is split into two parts, one for the server side and one for the client side, which distributes through the Fed server. This split ensures the client-side model is lightweight enough to run on resource-constrained devices. Next, the client-side model in the Fed server is distributed among all the clients as the global client-side model. In next step, clients pre-process their own dataset and then the client-side model perform a forward pass on that processed dataset. During this forward pass, a Laplacian noise is added to enhance the privacy. After completing the forward pass on the client side, the output from the final layer of the client-side model, also called as smash data, is then sent to the main server. Then the server model completes the forward pass and computes the predictions using the smash data received from the clients. Next, these predictions are shared with respective clients for the loss calculation, where each client calculates the loss and sends it back to the main server again. The server updates its model parameters based on the received loss from clients. And then the server computes the gradients of these smash data and sends it back to the respective clients. And each client updates its local client-side model using the received gradients. After each epoch, the updated client-side models are sent back to the Fed server. The Fed server averages these updates to create a new global client-side model which is redistributed to all clients for the next epoch. This process continues until the model is fully fine-tuned. Let's move into the demonstration. This provides a step-by-step procedure in preparing the server and client for the fine-tuning process. In here, the GPT-2 large language model is fine-tuned using DisLLM, and we have used Scam Dialog dataset from Hugging Face, which consists of 8 distinct classes. And in the experimental setup, the cut layer is positioned at second transformer block, and the complete process involves 5 client devices as shown in the diagram. And at the end, experiment results will be presented graphically.
Let's begin with loading the model to the client. In the model load function, we import the GPT-2 base model. The command includes true greater than null at the end to prevent any warnings from being printed in the terminal. The layers start with the token embedding layer followed by multiple transformer blocks. Here 0 is the first transformer block, 1 is the second, and so on. When we use print model function to visualize the architecture, you will notice that there are 12 transformer blocks in total. Now let's check the number of trainable parameters in this model using numparams function. It contains approximately 124 million trainable parameters. Here is where it gets interesting. We are going to apply a parameter vision fine-tuning method called LoRA using apply LoRA function. Watch what happens to the number of trainable parameters. They have been grammatically reduced to just 1.3 million. Now we are splitting the model using model split function. This function allows us to specify exactly how much of the model stays on the client side by passing a cut layer position argument. In here, if we set it to 2, you will see only 2 transformer blocks in the client model. Change that to 3 and you will have 3 transformer blocks in the client model. Now the client side model is configured. Let's focus on data preparation. We start by loading our dataset using the load dataset function. Here are the first 5 rows for reference. Then we can perform label encoding using label encoding function, followed by splitting the dataset into 3 parts: training, validation, and tests using the dataset split function. Next step is tokenization and sequence standardization. This process ensures all the dialogues in the dataset have a uniform length. We are setting each dialog to exactly 120 tokens, truncating longer sequences and padding shorter ones. Let me show you what first and second data point looks like after this pre-processing using train dataset element function. Final step is creating data loaders. Let's move to the server side. After the model loads, notice that the original model has 50,257 output features in its final layer. Since we are working on a classification problem with 8 classes, we have to modify the output head accordingly using modify out head function. Now, there is only 8 output features. After applying LoRA and splitting the model with model split function, we can see server-side model portion. In here, there are 10 transformer blocks. We can change the cut layer position, but anyway we need to set the same cut layer position for both client and the server. For the training process, we have implemented a distributed setup with 5 clients, a server, and a fed server. By observing the client training interface, you can see how accuracy improves throughout the training process. Thank you for your attention and have a nice day.